Welcome back. Today in this lecture, we'll be discussing about arithmetic pipeline, how you can design your own pipeline, what are the concepts that you should be familiar with while you are designing an arithmetic pipeline, what are the peculiarities of arithmetic pipeline, what are the components that you should be known while you are designing an arithmetic pipeline, so on and so forth. So before we start, we should actually refresh some of the concepts that you have learned in your previous course on computer organization. So let's talk about that as computer arithmetic principles. So when you talk about a digital computer, it actually the computers that we see in these days, they actually go for finite precision. So this finite precision means you cannot go for an infinite number of decimals or infinite number of exponents or fractions that can go for a particular number. It should be always within a limit, and that is called finite precision. Okay, because the digital computer which we see today are having fixed size memory. They will be having fixed size memory capable of storing fixed sized words. So when you talk about an arithmetic that has to happen based on this data, it should also be having a finite precision, which means there should be some mechanism to limit the data that is being available, or the limit the representation of the data. So as we all know, there are two types of components when you talk about the arithmetic. It should be either a fixed point or what we say the integer component, and then there should be something which will be handling all the floats, which we call the floating point arithmetic. Okay, so both fixed point and floating point arithmetics are supported by the processors that we see in the modern computers. So they actually have separate hardwares which are actually part of the same processor chip. So an integer unit hardware will be designed specifically to handle the fixed point arithmetic, whereas a floating point hardware will be designed specifically for handling the floating point arithmetic. Both of them in the recent computers, they are built into a single chip of the processor. Earlier, you actually had floating point separated as a co-processor, but in the modern computers, they are actually fit into the same processor chip but as separate hardware units. Then, as we know, finite means when you have to talk about the finite numbers or the fixed point numbers, you will have to actually truncate or round them into the limit when they are actually exceeding the limit which is given. So whenever you have a value which is exceeding the limit, you will have to truncate it and fit in to the limit that is being accepted. When you talk about the floating point, there is no truncation possible. What we actually do is you say that if an exponent is going out of the range, then we call that condition as an error condition, and we call it as an overflow or underflow, and you will stop the execution right there. So when you talk about the fixed point arithmetic, you would be remembering you can have addition, subtraction, multiplication and division possible as the primitive operations in the integers. So when you add two n-bit numbers, you will have an n-bit number as the result, but it can even have a carry, and you should have some mechanism to handle the carry. When you talk about the subtraction also, when you have two n-bit numbers to subtract, the result will also be an n-bit number. In the case of multiplication, when you are actually going to multiply two n-bit numbers, the results would be 2n bit valued. The result would be having 2n bit length. When you talk about division, the quotient can go for any arbitrary number of bits based on the divisor that is being used. So you can actually go and refresh yourself about all these concepts. You can refer to page number 275 in your standard reference textbook, which is given for this course, and you can just refresh your concepts that you have learned before we actually started with this module, and also the concepts that you have learned in the computer organization course. Now talking about the floating point, as we know, the floating point is represented as a combination of, there will be a base, there will be a mantissa, which we talk about mantissa as the fraction, and an exponent to this floating point number. So it will be like a combination of value, a decimal, or we say the base, then a mantissa, which is the fraction, and then an exponent value. Putting together, this is a floating point number. Talking about the operations, you can have floating point addition, floating point subtraction, multiplication, and even division. So how you do this, what are the changes that are to be made, everything you can just refresh for yourself. This is already taught in the computer organization course, but you can refresh those concepts again by looking into page number 276 in your standard reference book. Moving further, we have to talk about the arithmetic pipeline design. So when you talk about the arithmetic pipeline design, there are actually two types of arithmetic pipeline. You can have a static or scalar arithmetic pipeline and a vector arithmetic pipeline. So scalar, as the name says, the operands, the instructions should be scalar instructions. The pipeline would be working on scalar instructions, and the operands should always be scalar values. So what is scalar and vector? That is already being taught in the module number 2. So you can go refresh yourself for understanding those concepts again. Now talking about the static arithmetic pipeline, so you can have the arithmetic logic unit inside a modern computer. It can handle, as we all know, it can handle the fixed point operation as well as the floating point operation separately. Then when you talk about the scalar operations, the scalar arithmetic, then the instructions would be scalar instructions, the operands would be scalar operands, which means when you talk about a variable, it will be having only one value, not many values. But when you talk about the vector, you will be having multiple values for the same operand. So multiple values are put together to become one single operand, that is vector. So you know all those differences. So when we talk about the scalar arithmetics, you can actually create scalar arithmetic operations. You can create the scalar arithmetic pipeline, and to actually execute the scalar arithmetic pipeline, you can use something called a software loop. You can use that, and you can just make the instructions work. But when you talk about the vector arithmetic, you have to employ specific hardware, specialized hardwares which can actually execute the vector instructions. Okay, so this can be either associated with the scalar pipeline as an add-on, or it can be given as a separate unit. Okay, so the control will be either a hardware control or a firmware which is directly controlling the vector instructions. So this is something which you should know before we start with talking about the design of an arithmetic pipeline. So as I said, the vector hardware pipelines will be built as add-on options to the scalar processor, or it can be like an attached processor, attached separate processor, which is driven by something called a control processor, which is actually a hard-wired control. So the scalar and vector operations, you know how they differ. They differ in register files and also the control mechanisms. So the registers, in the case of registers, they will be having only one value to store in the case of a scalar instruction, the scalar pipeline. When you talk about the arithmetic pipeline or the vector pipeline, you will have multiple values being stored inside a single register. And also about the control mechanism, as I said, in the case of a scalar arithmetic pipeline, it is done using a software loop. In the case of a vector arithmetic pipeline, it can be either controlled by a specific hardware called a firmware, or it can be given as a hardwired control. So that is about the introduction to scalar and vector arithmetic pipeline. Now let's see about all these. So first we have to know what is CPA and CSA. This is also something which you have already learned in your course on computer organization. So CPA stands for carry propagate adder, and CSA stands for carry save adder. So when you talk about the arithmetic and logical shift, you have to make use of the shift register. Then you have something called the high speed addition, which can be either done using a CPA or a CSA. So if you are talking about the CPA, as the name says, the carry generated will be shifted or propagated from the right end to the left end, or from the least significant bit to the most significant bit of your result. Okay, so that's it. The successive digits, the carry generated will be propagated through the successive digits, and finally it will be taken to the part taken as part of the result. Okay, so you can either have a ripple carry propagation or carry look ahead propagation. All these concepts are actually taught. Actually, you have learned all these concepts in the computer organization course. So if you want to actually refresh them again, you have to just go recollect the notes that you have been given with for the computer organization course, and just rewarm your brain with such concepts again, so that you will understand it better. Now, this is an example of a carry propagate adder. So, there is two input A and B. A is given with a value, A is n bits and B is also n bits. The result, as you can see, the result is also of n bits. So, S stands for the sum. Now, there is a carry, and this is a carry propagate adder. So, the carry generated will be propagated through the successive digits, and at one point it will be given to a single bit as the carry out. Okay, so this is the result for the carry propagate adder. For A is equal to 1011 and B is equal to 0111, and this is the result. Talking about the carry safe adder, there you are not going to propagate the carry, but they will be stored as a separate vector called a carry vector. So you will be storing it as separate units. You will not be taking them into consideration while you are adding the successive digits. Thus carry generated will be right away taken to a vector called a carry vector. So you will have two outputs. First one is the bitwise sum and the other one is the carry or the carry vector. So here you can see it is actually having three inputs. So in the case of CSA, it has having three inputs. Okay. So in the three input, all the inputs are of n bits, and you can see the result is having n plus 1 digits, where n plus 1 stands for the final carry that may emerge. So this is the pictorial representation, and this is the explanation for the same. So you can see the leading bit of the sum will always be a 0, which is the leading bit. This is always be a 0, and the trail bit of carry will also be always a 0. So the carry trail bit is always a 0. Okay. So this is it. Now in the case of this n bit carry, x, y and z are three n bit input numbers, and the CSA is going to perform the bitwise operation simultaneously on all columns of the digits. Then whenever there is a carry, the corresponding carry vector, the corresponding bit in the carry vector will be given that value, and two output will be generated. The first output will be the original bitwise sum, and the other output will be the carry vector. So this is it. Now talking about the multiplication, as you can see here, multiplication, when you have two n bit values to be multiplied, the result will be 2n. So here you can see A and B, there are two values A and B. A and B are both 8 bits, but the output or the product is actually of 16 bits, because that is 2 into 8, 16 bits. Fixed point multiplication means you have to sum all the 8 partial products. So P0 is the first partial product, P1 is the second partial product, so and so. Adding all them, the bitwise sum of all these will give you the final product, and it will be of 2 into n, that is 2 into 8, 16 bits of length. So all these are actually basic concepts which we have already learned. We are just refreshing those concepts so that you can understand the concept of an arithmetic pipeline better. Now talking about this fixed point multiplication, what should be the pipeline for fixed point multiplication? So in the case of a pipeline for fixed point multiplication, you will need 4 stages: S1, S2, S3 and S4. So here we are talking about two values each of 8 bit length. Okay, so those will be fed into the first stage. Okay, so in the first stage, what happens? S1, in the case of S1, what happens is it is going to generate all the 8 partial products ranging from 8 bits to 15 bits simultaneously. So you are feeding into the stage two given values A and B. So all the partial products, as we have seen here, all these partial products from P0 to P7, that will be generated in stage 1. So this is stage 1. All those partial products will be generated. Okay, so all those partial products will be generated, and what happens? So you have 8 partial products. You will be feeding them into the second stage, where you have 4 units of carry safe adder. Okay, so you have 4 units of carry safe adder which are arranged into 2 levels, and what they do is that they will merge the 8 numbers. You have 8 numbers, 8 partial products. They will merge them into 4 different numbers. Okay, so the carry save adder will work. As you know, if you don't have n bits, you will have to make them n bits by adding zeros to it. So making all that done, this 8 partial products, which were ranging from, the first one was 8 bits and the last one was 15 bits in length, putting them together, you will merge them together as 4 different numbers. So out of the 8, now you have 4. Okay, so 4 different numbers. Then in the second stage, again what you do, you have 4 different numbers. You have 2 carry save adders. Those 2 carry save adders in 2 levels, they will merge the 4 numbers into two 16-bit numbers. Okay, so in the first stage is S1. It is using a multiplier recording logic, and it will generate all the 8 partial products. Moving it to the second stage, you have 8 different partial products. The first one having 8 bits and the last one having 15 bits of length. You will take them to the second stage, where you have 4 carry save adders, 2 each on one level. So you have 2 levels in total. In the second stage, these 8 partial products will be added, will be undergoing the carry save operation, and it will generate 4 outputs. The 4 outputs will be taken out and it will be fed into the next stage of the pipeline, where again the same logic is applied, but instead of 4, you have 2 carry save adders. The 2 carry save adders, what they do is that they will actually convert, or they will merge these 4 partial products from stage 1. It will be stage 2. It will be converted into 2 values, each of 16 bits of length. Okay, so in the stage 3, what happens is that the 4 partial products from stage 2 is converted into 2 partial products in the stage 3. From the stage 3, this is given to the final stage, which is stage 4. In the stage 4, you have a carry propagate adder, which is accepting 2 numbers, and those 2 numbers should be of 16 bits of length, because your initial values given in stage 1 were each of 8 bits. So the result should be of 16 bit. Now in the fourth stage, what you do is that you have received 2 outputs from the stage 3. It is taken as input to stage 4, and you have employed a carry propagate adder. This carry propagate adder will add those 2 numbers, and it will be converted into one single number of 16 bits of length along with a possible carry. So this is how multiplication is made possible, sorry for that, in the case of a fixed point uh, number, in the case of a fixed point multiplication. Moving further, when you have a floating point, so this was actually discussed in the previous example also, in the previous module also. So here we are going to discuss about the floating point functional pipeline, which is available in the case of Motorola MC68040, which was actually discussed in the case of the first module. Okay, so we were discussing about the functional units of MC68040 in module 1. Now we are going to see how to design, or how the arithmetic pipeline is being designed in the case of MC68040 from Motorola. So here the arithmetic pipeline is having 3 stages. Okay, 3 stages. The first stage, in the case of the first stage, you have the mantissa section as well as the exponent section. They both are implemented as 2 separate pipelines. So here you have, this pipeline is employed for the mantissa section. This pipeline is employed for the exponent section. Both of them are having 3 stages. This pipeline is for the mantissa section. It has got 3 stages. This pipeline is for the exponent section. It is also having 3 stages. Okay. So the mantissa section, what is it going to do? The mantissa section will perform the floating point add or multiply operation on either 32-bit or 64 bits of data. Now talking about The Mandisa section, we'll see each one of them in detail. So this is the pictorial representation. You have stage 1, stage 2 and stage 3. In the case of Mandisa section, in the stage 1, it will receive the input operand and returns with computation results. So it will receive the input operand. You are using 64 bits register. All three stages are connected using two 64-bit data buses. You can see two 64 data buses here. So they are actually employed to connect between the stages. In the second stage, so here the first stage it is receiving the input operands. In the second stage, you have something called a multiplier. So it is an array multiplier which is repeatedly used to carry out the long multiplication. So as I said, one input will be of 32-bit. So to handle such kind of a multiplication, you will contain an array multiplier which will be used repeatedly to carry out a long multiplication of two matrices. Now after this, you have something called a 67-bit adder. So you are generating something, the 67-bit adder is there. It is going to perform the addition or subtraction of the two matrices. So whether it be a multiplication or whether it be a division, it is actually nothing but addition or subtraction respectively of the matrices in the case of a floating point number. So you are going to do the same concept. You are using a multiplier. You will be generating the long multiplication. You will be doing that. After that, you will employ a 67-bit add unit which can perform either addition or subtraction based on the request. Now you are employing something called a barrel shifter which is used for normalizing the output. Okay. Then in the stage 3, this is the stage 3, the last level, you have registers which will hold the result. Then you have something called the incrementer which will help you to rearrange the output according to the expected value. Now, it contains the register for holding the results before they are loaded into the register file in stage 1 and for subsequent use by other instructions. So what happens here, the output was actually 67 bits. It was given through the barrel shifter and then it is given to the register as a 64-bit information. This 64-bit information is given to the register. It is stored inside that. This 64-bit information will be given as the input to the next instruction of the pipeline. So this is how the Mandisa section works. Now, as I said, the barrel shifter, it is a logic circuit which shifts a given word by a varying amount. You are not saying that shift by 1 bit, shift by 2 bit. Based on the request or based on the requirement, the barrel shifter will be shifting a given word by a varying amount of instruction as if it is given with. Then it will contain a control input to specify the number of bit positions that it should shift the word by. Then it is actually implemented with a sequence of shift multipliers, each shifting a word by 2 raised to k positions for variable values of k. So that is all about barrel shifter. Now talking about the arithmetic pipeline design, you have discussed about the Mandisa section. Now what remains is the exponent section. In the exponent section also there are three stages. In the so what happens is instead of a 64-bit bus, you are actually going to use a 16-bit bus. So in the first stage, it has got an exponent. That exponent adder is there. The exponent adder will be comparing the relative magnitudes of two exponents. So you have two exponents, x raised to y and x raised to z. Y and z will be compared and that comparison is going to happen in the first stage of exponent pipeline. In the second stage, the result of the stage 1, which is greater, whether it is y or whether it is z, that result will be given and based on that it will equalize the exponents before the Mandisa addition can be performed. Therefore, the output of the exponent adder is sent to the barrel shifter for Mandisa alignment. So as you can see here in the stage 2, this particular result will be aligned and that result will be given to the barrel shifter so that the barrel shifter will adjust the Mandisa accordingly. Now moving into the third stage after the normalization of the final result. So that is done using the barrel shifter and you can see the output goes back. So here you can see it is given to the input and the output goes back to the exponent pipeline. So after the normalization, the exponent is readjusted in stage 3 using another order and the final value of the resulting operation is fed from the register in the stage 3 to the register file back in stage 1. So this is about the exponent section. So that is actually given for the next instruction, not for the current instruction. It is this output is given back to the register file for executing the next instruction successfully. Now, when you talk about multifunctional pipeline, as the name says, it is going to have multiple functions, which means more than one function. So, you can even have a static pipeline or a dynamic pipeline. In the case of a static pipeline, it will be possible to handle only one function at the same time. In the case of a dynamic pipeline, you can have multiple functions performed at different times. So, a dynamic pipeline, as I said, it will allow several functions to be performed simultaneously through the pipeline as long as there are no conflicts in the shared usage of pipeline stages. So this is an example, this is a case study. So this is the case study of a TI bar ASC arithmetic processor. So you can see this is the pictorial representation. It has got 4 pipeline units. There is an instruction processing unit. So the instruction processing unit is responsible for handling the instruction fetch and decoding, and also all the operations of memory buffers and arithmetic units are controlled by the working register. So all these put together, it is the instruction processing unit. This one, instruction processing unit. You have got some registers, you have got some of the various types of registers, and it is responsible for fetching and decoding the instruction. Moving further, the next stage is the operand buffer. So as you can see, there are sets of operand buffers in each of the arithmetic unit, which is, you can see it is XYZ and X dash Y dash Z dash. So it will actually help you to get the corresponding operations. So here the input operand is taken as XX dash and YY dash, whereas the output results are taken as Z and Z dash. So this is about the second stage, the second unit, which is operand and buffers, operand buffers. Moving further, both the processor and memory buffers are accessed by the main memory. So this is the pipeline arithmetic unit, which is the third phase of the pipeline. So as you can see, there are 4 pipeline units: pipeline 1, pipeline 2, pipeline 3 and pipeline 4. All of them are accepting inputs from the operands and also the instructions from the instruction processing unit. So this pipeline is fetching the instructions from the instruction processing unit and also the operands from the operand fetch unit. So both the processor and memory buffers accessed the main memory for instructions and also for operands or results, making the main memory very much involved in the case of an arithmetic pipeline. So this is an example. Here you can see this is an arithmetic pipeline design. This is actually a pipeline arithmetic unit where you can see some stages and also some arrangements so that the stages can be utilized according to the functionality, whether it be addition, multiplication, division or subtraction. So in the case of this particular pipeline, it has got 8 stages. So first stage, it is going to accept the input. In the second stage, you are going to get the exponent as well as exponent. Then you can perform the subtraction. Then you can align. Then you can get the fraction, add them together. Then you can normalize. Then you can multiply the function if you require. Then you can accumulate the results, and finally you can give the output. Okay, so this is actually the pipeline arithmetic unit. It's actually part of the static multifunction pipeline, and since it is static, it can perform only one function in a given time. Then you can even perform both fixed point and floating point units, floating point arithmetics using the same pipeline. But as I said, one function at the given time. The PAU or pipeline arithmetic unit will actually support vector in addition to scalar instructions. Then different functions required different pipeline stages and different interstage connection patterns, thus leading to a delay in the proposed unit. So this is all about arithmetic pipeline unit. You can see it from the figure from the page number 274 in your standard reference textbook. You can go learn it. You can go read through the contents so that you can understand it better. Thank you.